So thank you, Antonio, for the very nice and thorough introduction. So yes, as I guess all of you know, I'll be talking about next generation time domain diffuse optics using superconducting nanowire detectors. Okay, so in this talk, I'll be going through a lot about how the technique works and the techniques that I'm using. But first, I want to start off by talking about what are the applications for these techniques that I will talk about. So the applications that we're talking about are these are optical techniques with the application of measuring regional hemodynamics non-invasively. So by hemodynamics, I mean blood flow as well as tissue oxygen saturation. And the nice thing about these measurements is that if you can combine blood flow with tissue oxygen saturation measurements, you can actually measure tissue metabolism. So as you might imagine, there are a lot of different clinical applications for the measurement of hemodynamics, including in the measurement of stroke patients, in the measurement of patients with a traumatic brain injury, cancer, maybe to look at how the brain develops in infants, in sports medicine, etc. So there's really a wide variety of clinical applications where the techniques that I'll be presenting might be relevant. That's not to say that these techniques are going to be that they are the only techniques that are able for measuring hemodynamics. That's far from the truth. There are plenty of techniques used in the clinics that are able to measure hemodynamics, including, for example, CT, PET, and MRI, and maybe a little bit more exotic is transcranial Doppler ultrasonography. So these techniques, I'm sure that you've all heard of them. While they work great, there are some limitations and drawbacks in these techniques. For example, they're not really portable. CT and PET scans require ionizing radiation, and these scanning methods really only take pictures of what's happening at one instant of time in the hemodynamics. It's not capable of taking continuous measurements. So that brings me to introduce these techniques that I'm talking about, which are called diffuse optical techniques. And they really have the advantage of being able to measure hemodynamics in a way that's portable, doesn't require any ionizing radiation, is capable of local measurements, and is also capable of continuous measurements. I added portable to this list. However, you might realize later on in this talk that these next generation techniques aren't quite portable. But in general, diffuse optical techniques, they are portable. And in fact, we're going towards wearable devices as well. Okay, so let's get started to talk about how these techniques actually work. I'll start off with the typical image of a hand covering a white light source, and you see that the hand glows red. So that red glow comes from the fact that we're taking advantage of wavelengths that aren't absorbed so much by the tissue. So in this case, the red section of the visible spectrum wasn't really absorbed by my hand and therefore passed through. The other thing to note here is that there's no visible structure of bones, and so we're talking about multiple scattered light that's detected by the camera. So all directional information is lost. So in all diffuse optical techniques, the setup looks quite similar. We have our tissue, that's the yellow box, that contains different scatterers, absorbers. We place a source on top of the tissue of interest, as well as a detector placed a certain distance away from the source. So for example, if I want to measure the brain, I might put a source and a detector on my forehead. The separation between the source and the detector is called the source-detector separation, or in this case, I annotate it as rho. The photons coming out from the source, a lot of them aren't ever going to reach the detector. A lot of them are going to be absorbed by the absorbers. However, some of them are going to be scattered through the tissue, taking a random walk through the tissue, and eventually be detected by the detector. So just to formalize everything, we also need to characterize the tissue that we are measuring, and we do that by defining the scattering coefficient, or μs. That's the probability per unit distance of a scattering event occurring. The reduced scattering coefficient, or μs prime, is the probability per unit distance of isotropic scattering, so all directional information being lost. And then the absorption coefficient, or μa, is the probability per unit distance of an absorption event occurring. So Once characterizing your entire system, you can actually calculate out the probability of where the photons that are eventually detected by the detector, what part of the tissue they have traversed. So when you do that calculation, the probability map looks kind of like a banana, so we call that the banana pattern. And interesting and important to note here is that the further away you place your detector from your source, as you increase rho, the depth of that banana pattern increases. So there's a higher probability that photons have traversed a deeper area of the tissue. And so you can formalize all of this in a photon diffusion equation. I'm not going to get into the details of that, but we can write out this equation in order to characterize the photon fluence rate, or the power per unit area of light. So diffuse correlation spectroscopy, or DCS, is a diffuse optical technique that is used to measure blood flow. So as all of the diffuse optical techniques, we are placing a source at the surface of the tissue and a detector, again, placed a certain distance away from the source. But important for diffuse correlation spectroscopy is that we're using a coherent light source at the source side. And as the photons are interacting with the tissue and they undergo all of these scattering events, there's an accumulation of the phase shifts, which leads to an interference pattern at the detector. And so I'm sure all of you are aware that that interference pattern would be called a speckle pattern. So if the scatterers are static, then the speckle pattern is also going to be static. However, if the scatterers are also moving, that's going to result in a difference in the accumulated phase shifts from a time t to a slightly later time t plus a delay time tau. And what we see then is a flickering of the speckle pattern. So that it seems like the speckles are moving. So the basis of diffuse correlation spectroscopy is to make use of the fact that the speckle pattern will flicker if there are moving scatterers. And so what we do is we take a single mode fiber and we track the speckle intensity of just one single speckle over time. From that information, we can calculate out the intensity autocorrelation function, or G2. So in a measurement, what we're measuring is, again, the intensity autocorrelation function, or G2. However, using a very simple relationship, we can map that intensity autocorrelation function into the electric field autocorrelation, or G1. And by the use of, well, the mathematical formulation of G1, which is very similar actually to the photon diffusion equation, we can get out information about the flow, and that's in this alpha dB parameter in the bottom plot here. So as flow increases, your electric field autocorrelation G1 is also going to decorrelate faster. So DCS works quite well. It's been validated against other gold standard techniques for the measurement of blood flow. However, there are some drawbacks to DCS. And one of them is that experimentally, we're often working in very low detected light conditions. That's due to many different reasons. One of them is that we're limited by the safety standards. So typically we use 785 nanometers and we can inject only 28 milliwatts of light. And also, we're often interested not really at superficial measurements. We really want to measure deeper structures. So for example, we want to measure the brain, or we want to measure the muscle. And that requires us to go to longer source detector separations, and therefore we detect less light at the detector. In addition to all of this, increasing the signal to noise ratio in DCS is not trivial. There's a relationship that maps SNR, the signal to noise ratio, with the number of detector channels. So to increase SNR, we really want a higher number of detector channels. But that's not really that simple, because the DCS hardware involves a single mode fiber coupled to a single photon avalanche diode. And then to increase the SNR, that would require just a lot more fibers as well as more detector channels. So upscaling a DCS system makes it physically very large. It also makes it very expensive, and it's not always easy to parallelize all of these independent channels. Which brings me to the next diffuse optical technique that I want to talk about, which are speckle contrast techniques. So these are techniques that use detector arrays to measure blood flow. So what happens in a speckle contrast measurement? We take an image of our speckle pattern using a detector array, so for example, a CMOS camera, with a certain exposure time t. And what we do then with those images, either we can spatially sample our pixels and get out the distribution of speckle intensities, or we could also take all of these images and then track a pixel in time and look at that intensity distribution of the speckles. Both of them are valid. So here you can already see that we're using detector arrays, and if we talk about CMOS cameras, we're talking about megapixel arrays. So we are increasing the number of detector channels in relation to DCS measurements. So what do we do with this histogram? Well, we calculate the standard deviation of the speckle intensity as well as the mean intensity of the speckles. And that ratio is equal to a parameter which we call kappa, or the speckle contrast. And in that is the information of the blood flow. So how is that all related to DCS? You can go through all the derivations, and we see that the squared value of kappa, so kappa squared, is actually equal to an integral where inside the integrand we have our electric field autocorrelation, which was the data type from DCS. So if we look at this integral a little bit more carefully, we see that we have G1 squared inside of it, and we're taking the integral over our delay times, tau, of the autocorrelation, from 0 to an exposure time of the camera, t. And typically we use exposure times of about milliseconds in speckle contrast measurements. And we can also show that kappa squared is inversely proportional to the blood flow. So while the detection scheme of speckle contrast techniques might look different from diffuse correlation spectroscopy, the information is all there. Okay, so now I've gone through diffuse correlation spectroscopy as well as speckle contrast techniques, speckle contrast optical spectroscopy. Now I want to talk about time domain methods. So using pulsed light, we can actually get out a lot of other information. I've been talking about continuous wave light up until now. So if we inject just a pulse of light with a width of, let's say, some 100 picoseconds, again, the photons are going to travel through our tissue, just like it did in the previous example. But if we also have a sync channel where we know when the laser pulse was injected into the into the tissue, we can also calculate when the photon was detected by the detector. So what we build up is a histogram of the distribution of what we call the time of flight of the photons. That will be broadened with respect to our input pulse. This DTOF curve, or the distribution of time of flight curves, contains information about our optical properties. So again, mu A as well as mu S prime. But also importantly, it contains information about the layers. So earlier photons are going to correspond to photons that have mainly traveled shorter photon paths. So that would relate to more superficial layers, while late photons will relate to photons that have traveled much longer photon paths and therefore have a higher probability of having been through deeper layers. So this is very important if we consider, for example, non-invasive measurements on the head. So if we are placing our probe directly, for example, onto the forehead, and we want to see what's happening into the brain, we might discard all of our early photons and only look at late photons to try to increase the sensitivity of the measurement to brain. Same thing, for example, in the arm or the leg, we might want to exclude all of the skin and fat effects and just look at information that is more pertinent to the muscle. So by using this pulsed light and time domain techniques, we can combine our diffuse correlation spectroscopy as well as speckle contrast optical spectroscopy, and we get out time domain diffuse correlation spectroscopy and time domain speckle contrast optical spectroscopy. So another thing that we could do is we could also consider the wavelength that we are using in DCS. So typically in DCS experiments, the traditional wavelength that is used is 785 nanometers. That's advantageous for various reasons. We can use standard detectors, but as I already said, the maximum emissable power is around 28 milliwatts. So there's been ideas that maybe we should try to go out to longer wavelengths. And the advantages of going out to longer wavelengths is that we have more photons per unit energy, we have a higher penetration depth, we also are able to use we can inject higher powers of light into the tissue. So instead of 28 milliwatts, we can inject 103 milliwatts. Also, as a side note, going to longer wavelengths actually means that we'll be less influenced by the melanin, so skin color will be less of an influencing factor. The downside of going to these longer wavelengths is that we might have to start using less conventional detectors. So what kind of less conventional detectors? I'll be talking about superconducting nanowire detectors. So superconducting nanowire single photon detectors, or SNSPDs, work basically inversely to what a typical detector does. So in a typical detector, you measure a current whenever a photon hits the photosensitive material, but in the SNSPD, you always have a current and you measure the resistance when light is incident onto the nanowire. So how does that work? Well, we have a nanowire that's cooled down to superconducting temperatures, and we apply a bias current across this wire. If a photon impinges onto the nanowire, then it forms a resistive hotspot. And due to this resistive hotspot, this forces the bias current to go around the hotspot, increasing the current density. When the current density gets higher and higher, it will at one point break superconductivity and create a totally resistive barrier. After some time, that superconductivity will eventually be recovered, and the detector will be ready to detect another photon. The really nice thing about these superconducting nanowire detectors is that they have negligible noise. They have very high quantum efficiencies at more exotic wavelengths, so beyond 1000 nanometers, and they also have a very high temporal resolution. So now let me talk about the PolyMe and ICFO joint lab. This is a joint lab that was developed within the framework of Laserlab-5, joining the competencies of PolyMe, where they are the experts in time domain diffuse optics, so these pulsed light source techniques, and ICFO, which has expertise in diffuse correlation spectroscopy and non-invasive blood flow measurements. So within this PolyMe ICFO joint lab venture, there have been several research projects that have been carried out, and now in the next few slides, I want to introduce some of the results from those projects. So starting off, we had the first demonstration of time domain DCS in humans. This was done by Marco Pagliazzi. He was a PhD student at ICFO, but thanks to the joint lab and the experimental setups at PolyMe, he was able to take these measurements, and he showed that by taking gated, so by selectively looking at the muscle and getting rid of all the skin and the fat layers, he could see that there was a higher response to blood flow after an arm cuff occlusion. So let me explain this plot a little bit. In the very beginning, so around 3 minutes, you have a flat baseline value of blood flow. He had placed the probe on the forearm right here, and he had an arm cuff placed around his arm. So when the arm cuff was inflated, that didn't allow blood to flow into where the probe was located, and that's why you see this drop in blood flow. And then after a certain amount of time, the cuff was released, and that allowed the blood to re-enter the forearm, and that's why you see this huge peak in the blood flow. And as you can see in the gated case, there's a larger peak compared to the ungated case, and that's expected since the gated photons are predominantly from the muscle. Another example of results from the joint lab is the result of temporal speckles. So this was formed part of the thesis work of Lorenzo Colombo at PolyMe. And using the superconducting nanowire detector, he could see that in the DTOFs, there were ripples that were shown inside of rigid solid phantoms. However, these ripples seem to disappear in the liquid phantoms. So then the hypothesis came about that perhaps these ripples that are directly seen in the DTOF without having to take autocorrelation, with having to reprocess the photons into an autocorrelation curve, perhaps just from these DTOFs, there could be some information about the flow. So he proved that in his publication in APL Photonics. Another result from Lorenzo Colombo is time domain DCS at longer wavelengths. So the first result that I showed from Marco Pagliazzi, the first demonstration of time domain DCS in humans, was done at 785 nanometers. In this case, Lorenzo went out to 1000 nanometers and demonstrated that both in the early and the late gates, he could see these expected responses in blood flow in the same arm cuff protocol. And then finally, I want to show also this result from Veronica, who was a PhD student at ICFO. And in this case, she was measuring the brain, where this is data showing, this is a time trace of blood flow data taken in the brain when a subject was asked to do a Valsalva maneuver. So that's breathing against a forced, closed airway. So it's less easy to explain, but you have a flat baseline period, and then you have these ripples in the blood flow. That's the y-axis. And these ripples, they correspond to changes in the blood pressure. What is seen here is that in the earlier gates, these ripples seem to be a lot stronger, whereas in the late gates, the ripples seem to be much weaker. And that might be an indication of a cerebral autoregulatory effect. So in a sense, this might prove that the later photons do indeed originate more from the brain than the early photons. That's not to say that we're the only people doing time domain DCS. There are other initiatives that are very similar to our joint lab. For example, Harvard Medical School as well as MIT were actually the first to demonstrate path length resolved DCS using pulsed light. There's also another group in Poland that is also working on gated analysis of time domain DCS in humans as well as in phantoms. So we are not alone. Now, just to wrap up, I will introduce the recent FastMod project. FastMod is an EU-funded project born from the Polyme and ICFO Joint Lab Framework. We are 5 partners, mainly from academia, including besides Polyme and ICFO, including also TU Delft as well as UCL. And then we have an industrial partner, Single Quantum, also located in the Netherlands, and they're the ones that are developing the SNSPD detector. And then, of course, Laserlab for dissemination, exploitation, and support to management. So FastMod, unfortunately, I'm not going to show many results from FastMod due to the fact that it's a pretty young project still. But what we aim to do is to develop a 10,000 pixel single photon camera using superconducting nanowires. So this will be, quite a technological advancement to allow us to do also time domain SCOS measurements, not only DCS. We're developing new strategies for the readout and processing of time domain SCOS signals. We also have different simulations that we are running in order to propose the ideal sensor characteristics, as well as analysis methods. We want to create a fully automated 3D tomograph integrating time domain SCOS and time domain NIRS. And in addition to all of this, of course, we're going to validate all of our technology in the lab, including phantoms, as well as in vivo pilot studies. And that's all from me. Thank you very much for your attention. And thank you also to everyone from the FastMod Consortium and everyone else who has been involved in these projects and whose results I've been able to share today.